हेलो प्रोफेसर।
हेलो, हाय हसन।
सॉरी सर, एक्चुअली हुआ ये कि आपको मैंने ईमेल किया, आपका रिप्लाई नहीं आया, तो मैंने मुझे लगा कि शायद आज का लेक्चर पोस्टपोन आप कर देंगे या होगा नहीं, इसलिए बच्चे नहीं आए। लेकिन बच्चे आ रहे हैं। आई हैव इन्फॉर्म देम ऑन द ग्रुप। मेरा ख्याल है विद इन 5 मिनट्स या 7 मिनट्स वो ज्वाइन कर लेंगे।
सही सही। असल में हाँ, मुझे ईमेल असल थोड़ी देर से मिली क्योंकि मैं सो रहा था, थोड़ी देर से उठा हूँ।
ओह परफेक्ट सर, राइट।
कल मुझे ईमेल कर देते तो मुझे पता चल जाता, लेकिन लास्ट टाइम मैं रिप्लाई नहीं कर पाया क्योंकि मैं मसरूफ हो गया था। और मैं समझा
जी
शायद ये आई थिंक ऑब्वियस होगा कि आज मीटिंग होगी।
हाँ, सॉरी सर, एक्चुअली मेरी थोड़ी गलती है इसमें। तो अभी वो सर 5 मिनट में ज्वाइन कर लेंगे।
तो अभी तो मेरे ख्याल में मुश्किल हो जाएगा क्योंकि काफी लोग नहीं होंगे ना।
सर आप देख लें 5 मिनट में कितने लोग ज्वाइन करते हैं। अगर ज्यादा नहीं करते तो फिर हम इसको, आप देख लेगा, पोस्टपोन कर सकते हैं या जैसे आपको बेहतर लगे।
सही सही। अच्छा मुझे बताओ, इंडिपेंडेंट स्टडी का क्या सीन होता है यहाँ पे? हाँ सर।
हेलो, जी जी सर, सॉरी सर।
मैं कह रहा हूँ
इंडिपेंडेंट
ये
स्टडी,
इंडिपेंडेंट स्टडी का क्या सीन होता
जी जी सर, इंडिपेंडेंट स्टडी सर ये होता है कि आपको प्रोफेसर ऑफर करता है, लेकिन प्रोफेसर को जो है वो कोई कंपनसेशन नहीं मिलती है। मैंने अभी रिसेंटली फॉर 2020 सेमेस्टर में प्रोफेसर खुर्रम रहमान है, उनसे ऑफर करवाई थी
है?
इंडिपेंडेंट स्टडी स्टैटिस्टिकल मैकेनिक्स पर।
राइट।
क्योंकि कोई फैकल्टी, कोई स्टूडेंट सीधे ज्यादा लेने के लिए मतलब 15 रिक्वायरमेंट होती है, तो सारे स्टूडेंट्स थे नहीं उसमें, उसके लिए तो मैंने फिर उनसे बात करके इंडिपेंडेंट स्टडी ऑफर करा दी थी। तो उसकी मिनिमम लिमिट नहीं होती स्टूडेंट्स की, वो 2 या
सही
1 स्टूडेंट के साथ भी हो सकती है।
सही
तो
सही।
वो मैंने ऑफर कराई थी। तो उसमें होता है कि सर स्टूडेंट ज्यादा वो लेते हैं, इनिशिएटिव लेते हैं। तो हम लोग
अच्छा
बुक्स, हमने सजेस्ट की थी बुक्स डॉक्टर खुर्रम रहमान को। वो सिर्फ हमें देखते थे कि सुपरवाइज करते थे कि हम क्या कर रहे हैं क्लास में।
ठीक है।
सर आप ऑफर कर रहे हैं इंडिपेंडेंट स्टडी?
नहीं नहीं, मुझे ईमेल आई थी एक स्टूडेंट की, वो पूछ रही थी कि इंडिपेंडेंट स्टडी ऑफर हो सकती है क्या?
हाँ राइट सर, परफेक्ट।
तो कोर्स का मैं सोच रहा हूँ, अभी मुझे टाइम ही नहीं मिल पा रहा, लेकिन अब काफी लेट होता जा रहा है। मैं सोच रहा हूँ इस 1-2 हफ्ते के अंदर अंदर कोर्स डिजाइन करके इनको सेंड कर दूं, अगर अप्रूव हो गया तो।
सर आई सी सर, द प्रॉब्लम इज यहाँ पे अप्रूवल में बहुत मसला होता है कोर्सेज की। यूजुअली जब हम लोग को कोई कोर्स सजेस्ट करना होता था तो हम लोग पिछले सेमेस्टर के पहले दिन या शुरू के वीक्स में कर देते थे। बट इट्स
अच्छा, तो अब
सरप्राइजिंग
लेट
इफ
लेट
यू आर
लेट लेट
सजेस्टिंग।
तो नहीं हो गया होगा?
आई थिंक शायद से।
लेट हो गया ना?
बट सर लेकिन आई थिंक इफ अ प्रोफेसर इज वांटिंग टू ऑफर अ कोर्स, वो डिफरेंट होता है बनस्बत के अगर स्टूडेंट्स कहें कि हमें ये कोर्स ऑफर करवाना है।
राइट राइट। तो तुम्हारे सेमेस्टर खत्म हो गया?
जी नहीं सर, अभी चल रहा है।
तो कब एंड कब है? एग्जाम्स कब होंगे?
बस सर होने वाला है, ये ट्यूसडे को लास्ट हमारी क्लास है।
अच्छा, ट्यूसडे को है लास्ट।
सर मुझे आपसे बात करनी थी एप्लीकेशंस के बारे में भी।
हाँ हाँ।
अभी क्योंकि स्टूडेंट्स नहीं आ रहे, 1-2 स्टूडेंट्स वहां से आ रही है, सो
Yeah, sorry, I was eating lunch real quick.
नो प्रॉब्लम। सो हसन, क्या बात करनी थी?
सर मैं बॉन यूनिवर्सिटी अप्लाई कर रहा हूँ फिजिक्स के मास्टर्स के प्रोग्राम के लिए।
सही, ठीक है।
बॉन, आप बहुत सुनी आपने?
हाँ हाँ मैंने सुनी हुई है, अच्छी यूनिवर्सिटी है।
अच्छा सर, आपको क्या लगता है मेरे चांसेस क्या है वहाँ पे?
तुम्हारी जीपीए क्या है अभी?
3.3।
यार आई डोंट नो, मुझे मैंने बॉर्न यूनिवर्सिटी में शायद तो अच्छी यूनिवर्सिटी है, अप्लाई कर दो। मुझे यूरोप की यूनिवर्सिटीज के बारे में नहीं मालूम कि उनका क्राइटेरिया क्या होता है, कि कभी हो भी जाता है कभी नहीं भी होता।
आई सी। सर मैं अपना आपको मोटिवेशन लेकर भेजूंगा, तो आप मुझे उस पर फीडबैक दे सकते हैं आज थोड़ी देर में अगर भेज दूँ?
डेडलाइन कब है सबमिट कराने की?
आज ही है सर।
तो इतनी लेट क्यों की, पहले भेज देते।
सर एक्चुअली मुझे मैंने गलत देख ली थी डेडलाइन 1 जून को, मुझे लगा 1 जून को है, लेकिन एक्चुअली वो थी 1 मई को, तो इसलिए।
हाँ चलो सेंड कर देना, इसके बाद सेंड कर देना, मैं कर दूंगा।
ठीक है, थैंक यू सो मच सर। सर स्टूडेंट्स आर स्लोली ज्वाइनिंग इन।
मैं जरा पीडीएफ देख लूं कि पीडीएफ जो लास्ट टाइम मैंने करवाया था वो किधर मैंने सेव किया हुआ,
तो सर
तो वो मैं फिर आप लोग को सेंड कर दूंगा। Okay, so I have attached the last week PDF here. Last week PDF, I did not have a lot of slides. I think there are only few slides. But, okay, so I think we can start. We can start discussing any questions you guys have regarding the last, not last week, but the last week lectures. So I'm thinking today, okay, what I can do, I can give you like some taste of technical stuff in cosmology, some basic cosmological equations. What do you think? Do you want me to talk more about the other things, or do you want to see some equations and try to learn some equations?
sir, I personally want to see some equations.
What about others?
Yeah, I agree too. I think that's good.
Okay, so let me connect to my iPad. Can you allow me to share my screen? My screen sharing is disabled. Hassan?
Sure, sir. Give me a minute. So I've asked him, Mark, he help you become the host in just 2 minutes. But it'll take him 2 minutes.
Mm-hmm. So how many of you know special relativity? I'm not talking about general relativity or cosmology, but just special relativity. It's a so space and
So should we just raise our hands?
yeah, just raise your hands. Say if you want to say anything.
I do.
Okay, so can anyone tell me what the special relativity is? Like anyone who has raised the hand.
I'll give a try, but I don't know if I'll do it correctly. So
Sure.
special relativity is the, well, I think it's still a theory technically, but it's a theory that space and time are not two independent subjects. They rely on each other, and
Right.
time is actually a dimension, and your movement in objects in space could affect the way time moves, or the way time progresses, or actually the pace that time progresses, and mass could actually change space itself.
Right. Okay. Very good. So I am sending you some PDF on special. Yes, sir.
It's fine. I just wanted to respond to your question, but it's okay.
Okay, so I have shared a so very good notes. It's an undergraduate level note on special relativity. I sent you all other notes as well on cosmology, which I think will be nice for you. So what I can do, I can give you a little bit overview of what special relativity is, like very quick, very brief overview, and then we will jump on cosmology, because special relativity I think is very important to understand. Uh, uh, and at least to see how the equations look like. So I'm going to share my screen. No, not
You
this
can
one.
share now. Yes, you have been made co-host.
Okay, so screen share. Okay, can you see my screen now?
Yes, sir. We can see that you have got notes open up.
Okay, so I'm going to write here. So if you have any problem, anyone has any problem or suggestions, please feel free to tell me or ask any question. Regarding the notes, I will share the notes later, and please interrupt me here. Don't wait until the last moment to ask any questions. If you don't understand me, just ask me the question. So here very briefly. So I'm not going to take a lot of time today. So I think we have already wasted like 15 minutes, but at least I will take 1 hour. If you give me 1 hour, 15 minutes, I'll talk about special relativity, and 45 minutes, or maybe 30 minutes, I'll talk about cosmology. And then 15 minutes, we can just do some more discussions. So what is special relativity? I mean, the special relativity is again the theory that replaces the Newtonian mechanics, right? So the Newtonian mechanics, everything was deterministic. I mean, I'm not going towards probability, but in Newtonian mechanics, things depends on space and time. The physics depends on space and time, but this time and space were the independent quantity, right? But space plus time, right? What special theory of relativity is, it actually just replaces the Newtonian mechanics, and it says that space and time are not independent quantities, but they are the same quantity, right? So special relativity and Einstein said that space and time is basically the same quantity, which you can call space-time. The effects of special relativity become apparent only when the speeds of particles are very comparable to the speed of light, right? So if something is moving with a normal speed, 2 km/h, you cannot see the effect of special relativity. You cannot see how space and time are the same quantity. This effect is only obvious when you move with the speed close to the speed of light. One thing in special relativity, and there are some axioms. So axioms in mathematics are just the statements that you cannot prove, and you have to believe, and you build your theory on based on those assumptions. And one of the assumptions in special relativity, you assume that speed of light is constant in vacuum, and if you measure the speed of light, this is 2.99 × 10⁸ meter per second, right? So this is the speed of light. So first thing to say is that the speed of light is very fast, really fast. So the speed of light is around 300 meter per second. The escape velocity, if you want to escape the surface of the earth, is just 10⁴ meter per second, right? So if you compare the escape velocity with the speed of light, it's extremely fast. The orbital speed of our solar system in the Milky Way is around, so orbital speed of our solar system around the Milky Way is 10⁵ meter per second, right? If you compare this speed of light is really, really fast. So there are two postulates that I told you. The postulate number one, the special relativity, the laws of physics are the same in all the inertial frames, right? The second postulate is that the speed of light in vacuum is the same in all the inertial frames. So these are the two postulates of special relativity. So on the face of it, the second postulate looks nonsensical. The speed of light in vacuum is the same in all inertial frames. How can the speed of light look the same in all inertial frames, right? If light travels towards me at speed c and I run away from the speed from the light at speed v, surely I measure the speed of the light as c minus v, right? So if, for example, the light is coming towards me with a speed of light c, and here I am, right, and moving towards the light with a velocity v, so I should if I move away from this, so in my reference frame, what I should observe, the speed of light observed speed of light should be c minus v, right? But this is not the case. Special relativity says that in all the inertial frames, whether I am moving or not moving, I will always see the speed of light constant. I will always observe whether I am moving with velocity v, my speed of light that I will observe will always be c, not c minus v. So what does it mean? I mean, this common sense view is encapsulated in the Galilean transformation. So in mathematics, you do transformations, right? So you have this one coordinate system, you transform this one coordinate system to another coordinate system. And this transformation is called, okay, coordinate transformation. There is one thing called Galilean transformation. So in Newtonian mechanics, you fixes the time, right? So what happens is that there's something called Galilean transformation. So in Galilean transformation, mathematically what happens is if you have the two inertial frames, so call it S and S prime. So inertial frames are the frame of observation, right? So I am observing something, so I am teaching you guys. So what I am observing is my inertial frame. What you are observing me is your inertial frame, right? So whether I observe the universe or you observe the universe, the laws of physics should be the same for both of us in both the inertial frames. So whether I observe the speed of light or you observe the speed of light, or whether I am moving and observe the speed of light and you are moving and observe the speed of light remains the same. This is what special relativity says. And there are these two inertial frames, and they are relatively, they are moving, right, with some speed, and their relative speed, let's say one is moving towards the other. Right, so this is S prime, and this is S, and their, say, velocity is some velocity v00, right? So it's just one dimension. Maybe suppose they're just moving in one direction, so velocity only has one. So the Cartesian coordinates from one observer to the other observer will become like, so x prime will be x minus vt, where v is just the relative velocity between the s and s prime. So the prime coordinates belongs to the prime inertial frames, and not prime coordinates that belongs to the s inertial frames. The y coordinate remains the same. The z coordinates remains the same because the movement is only in the one direction, and the time remains the same for both of these, right? So this is the transformation. This transformation is called the Galilean transformation, right? So generally, whenever you have the two observable moving towards each other, we do the transformation like this. So if a ray of light travels in the x direction in the s frame with speed c, then it traces out the trajectory x divided by t. So suppose if a light ray, instead of the reference frame, if the light ray travels with the speed of c, then I should be able to call x divided by t is equal to c. So how much time it takes to reach and how much distance it has covered, x divided by t should be equal to the speed of light. The transformation above, this transformation, then tells us that in s prime, the trajectory, if the light ray is, so suppose in s prime, and this is a bit boring, I know, but you will see the result where I'm going. In s prime, you will see x divided by t should get c minus v, right? So this is the result we claimed above. We claimed that in my reference frame, I should get this result, right, when I'm stationary. But if I am moving towards away from the light source, I should observe the c minus v, right? This is the result we claim. The speed of light should clearly be c minus v, but this is wrong. This is wrong, and it is wrong. It is not right. Something must be wrong with the Galilean transformation, right? And I claim that this is wrong. If this is wrong, then Galilean transformation is not right. So this transformation has some problem. If I am, and this is wrong, then this transformation is a problem. And this is the transformation we use in the Newtonian mechanics. This is what I call the Newtonian mechanics. We always use this kind of transformation. आपने जो भी Newtonian mechanics courses पढ़े, you always do this transformation in Newtonian mechanics. But when things are moving really fast, like the speed of light, I'm telling you that this Galilean transformation is not right. So what is the right transformation when things moves with incredibly fast speed? Okay, and this is the start of the of the general relativity, special relativity, and there is a transformation called Lorentz transformation. Actually, Einstein, a fun fact, Einstein gave his theory of relativity in 1905. But Einstein was not the first person who came up with the idea of special relativity. Lorentz was a mathematician, and he already had the equations available for the transformation used in special relativity. So technically, Lorentz should have arrived at the special theory of relativity earlier than Einstein, but just because he was a mathematician, he was asking questions from a mathematical point of view and not the physical point of view, he was not able to arrive at the conclusion. But Einstein asked the right question at the right time, and he was able to give the theory of special relativity. But before Einstein, Lorentz already had the equations for these transformations. So what Lorentz says is that we stick with the idea of two inertial frames, right? So we have S and S prime, and they are moving relative with a relative speed v. Okay, so both inertial frames come from Cartesian coordinates. So we stick with S depends on x and t, S prime depends on x prime and t prime. Okay, so we want to know how these coordinates are related. So S and S prime. The most general possible transformation I can write is S prime is some function of x and t, and t prime is also some function of g of x and t, right? So these are the most general transformation. If Galilean transformation is not right, in order to write the most general transformation, I can say, okay, the x prime is some function of x and t prime is some function of x and t as well, right? And this could be anything. I mean, I can choose a function called some alpha 1x plus some alpha 2t, right? I can also choose some different coefficients, like on x alpha 3x plus alpha 4t, right? So I can choose x, this function f and g, whichever I want, right? And this function xi depends on the velocity, because these velocities, these coordinates are moving with the velocity, so they should depend on the velocity. Okay, so I'm not going on the details. So all the details are available in the notes. What I can tell you is that, I mean, if you stick to this transformation and derive the equation carefully, what you will get is a transformation when x prime is equal to some gamma times x minus vt, where gamma is some coefficient, and gamma depends on some velocity, relative velocity, and similarly you okay, so this is what we get. And yeah, Hassan. Yes,
Sir,
Hassan.
just wanted to confirm, x prime is the coordinate of the moving frame, right?
Yeah, so both are moving frame. V is the relative velocity. So it could be that one is not moving and the other is moving, or it could be that both are moving, but the relative velocity is V.
Okay.
Okay. Right.
But x prime, t prime, these are coordinates and parameters of which frame then?
So
This frame could either be moving.
if you have x prime, if you have x, then this coordinates belongs to this and this coordinate belongs to this. It could be that this is moving, this is not moving, but the relative velocity is just
Oh,
v.
right. Perfect. Got it, sir. Thank you.
Okay. So this is what happens. And if we do not have time to derive here, but I can just give you the equation that if you stick to this Lorentz transformation and derive things which are given in the notes, what you arrive is something like this. So your x prime is equal to some gamma times x minus v of c times c of t. Okay. And y prime is equal to y, and z prime is equal to z, and c of t prime is equal to gamma of c of t minus v of c times x. Okay, and these are where gamma is given like, so where gamma is square root of 1 divided by 1 minus v squared over c squared. Okay, so cool. So this is the equation which you can see in Galilean transformation. So c is the speed of light, v is the relative speed, gamma is a constant which depends on this this relative speed, and x and t are the coordinates. Okay, so if you want to go from one coordinate to another coordinate, and this transformation is generic, and you can see that if your speed is very small, right? So if, for example, v of c, so c is the speed of light, v is the relative speed. If v is very small, this transformation will become the Galilean transformation, right? So if you want to use the most generic transformation, whether your speeds are small or your speeds are not small, you can see that if v of c is very small, this gamma goes to 1, right? If gamma goes to 1, then this transformation will become the Galilean transformation. Exactly. And in the physics language, these are Lorentz boosts. Right? These are called Lorentz boosts. Okay, good. So, and you can see that in this equation, you can see that space depends on the time coordinates and the time depends on the space coordinates, right? So in one frame, you can see this depends on this, and x depends on these things. And this is the reason, and this is the basis of the special relativity, which says that okay, everything is linked. Space and times are linked together. Okay, cool. In space, in cosmology, also in general relativity, space-time diagrams are very important. Space-time diagram are very important. So if you have a diagram like this, so if you have CT, if you have X, and you have the particle right? So this is called the world line of the particle. The particle move in this trajectory, right? But if you have the light ray, then light ray in this thing always travels at the 45 degree, right? So this is the light ray. So this is X, this is CT. So light rays travels at 45 degrees in the space and time. Okay. So whichever you do, and you can read the notes, and I think it's very straightforward. Then how to see the space-time diagram. It becomes very, if it becomes then things will be quite straightforward to understand, because in cosmology and general relativity, we always play with space-time diagrams. Okay.
So what is exactly a world line?
So world line is just a trajectory, how a particle, it could be anything. I mean, it's not, this is just an example. It could be anything. It could be like this, okay? So it could be anything, but it should not be the speed of light. The speed of the trajectory at any point should not be the greater than the speed of light.
Oh, right, perfect, sir. Thanks.
But it could be anything. So this is what it is. One thing which is very important, and world line actually gives you also the concept of the geometry of the space and time. And one thing is very important is the invariant interval. So if you have 2 points in the space, you can say if these 2 points, what is the distance between these 2 points, right? So the distance between these 2 points, if you're in the Cartesian coordinate, then these are the Cartesian distance, right? And it has its implication. If you do any transformation, the Cartesian distance always remains the same, right? If you go from one coordinate system to another coordinate system, suppose your length of the vector will always remains the same, right? So that's maybe this length or of the vector or the distance between two particles. These are the invariant intervals in the Galilean transformation, but not in the Lorentz transformation. Lorentz transformation, what is the most invariant quantity? So is the following. So for example, I say in frame S, two events, P1 and P2 have these coordinates, CT1, X1, and CT2, X2. Okay, and these two coordinates, these two events are separated by this time interval. Okay, so one event happened maybe in the far past and the other event happened today, but just the separation is P minus 2, and the X is X1 minus X2. Okay, so it could be that one event happened tomorrow or yesterday, the other event happened today, and one event happened in Pakistan, the other event happened in maybe Caribbean. Okay, so just think about it. So X and T are two different separate events. Well, whichever event, whichever space-time coordinate they had in the universe, wherever in the universe these events happen, the invariant quantity interval, which we define by S square, is the measure of the distance between these 2 points. Okay, and this is equal to C squared delta T square minus delta X squared. And this quantity always remains the same in every coordinate. So whichever coordinate system you choose, this will remain the same. Here, X is just one system. If you have the 3 dimension, you can write C squared delta T square minus delta X square minus delta Y square minus delta Z square, right? And delta is the change. If you use the differential equation, differential system, then you call it ds square plus c squared dt square minus dx square minus dy square minus dz square. Okay, and And this defines the space-time of special relativity is topologically R4. So if you are interested in mathematics, so the topology of space-time is R4. Okay, so there are two things just to mention, because whenever you read the books, you will see two different definitions. You see, one is this. The second one is d squared minus c squared dt squared plus dx squared plus dy squared plus dz squared, and both are the same quantity. And this minus sign, whether minus sign comes with the time or the space, are just the two different conventions. So this is basically defined. This is called the metric space-time. Okay, and this metric defines the geometry right. So right now our geometry is R4, which is a spatial flat geometry. Nothing fancy is happening. Everything is flat. In this flat geometry, our metric is like this. Generally, in the convention, we define the metric like plus, minus, minus, or eta is equal to minus, plus, plus. So you will see the convention. If you see your metric is plus, minus, minus, then you will use this guy. And if you say your metric is minus, plus, plus, you will use this guy. In other way, you can also define eta is equal to minus 1 minus plus 1 plus 1 plus 1 0 0 0 0 0 0 0 0 0 0 0 0. Okay, so this is also another way of writing what your metric is, and also again you can just flip the sign. Okay, so both of these things. So this is just a metric notation. In the metric notation, you just take the eta, which is this thing, and yeah, so sorry, I'll not, okay, in the metric notation, you will write mu and mu, and your ds square is equal to mu nu, dx mu, and dx nu, where this d mu, where x mu, right, is the 4 vector. 4 vector is just like the 3 vector, but it depends on the time coordinate, which you call x naught, and the spatial coordinate. So whenever you see the 4 vector, you have the first vector is this time coordinate, and the second one is just the space coordinates. And this mu and nu here are the notation which defines these things are the 4 vectors. Well, so this is just a compact notation. This is just a compact notation of writing the invariant interval. I mostly use minus plus plus, so most of them use minus plus plus. So this is just a very concise geometrical general relativistic way of writing this thing. Okay. So this is all about spatial relativity. If you have understood these things, it would be pretty easy to understand the geometry of spatial relativity and cosmology. So just give me 5 minutes and then we can do the discussions, 5 and 10 minutes, 10 minutes actually, because I want to link the spatial relativity with this thing. So one of the idea of the spatial relativity is this thing. So time is the constant in the two inertial frames. Speed of time is the same. and you have to use this Galilean transformations and the concept of word lines, and the invariant interval is very important. Okay, so this invariant interval is really very important in relativity. Okay. So what happens is, like, what is the difference between general relativity and the special theory of relativity? In special theory of relativity, the underlying space-time is flat. Okay, so this is just the flat space-time. This is the R4. But in general theory of relativity, you can define any space-time. You can define any geometry. Your geometry could be curved. Your geometry could be like this. Your geometry could be like this. So any geometry you can define in. Hello, can you see my screen? I think the screen is not.
Yes, sir. I can see your screen, but your video is lagging a little.
Okay, okay. So your geometry can be anything. Special theory of relativity, general theory of relativity, GR. So in GR, you could be you have to use non-Euclidean geometry. Basically, non-Euclidean geometry has the spherical geometry, is a hyperbolic geometry, a flat geometry, everything. So I'm not going into the details of the general theory of relativity. What I'm going to do is tell you about what the space-time looks like. So in the flat space, so the geometry of the space-time. So for example, if you have the flat space, then the distance is like this. Okay, I'm not considering the time coordinates. And if you do the transformation, if you go from Cartesian to polar coordinates, you can write dr square plus r square d phi square. And this is very important because in cosmology, I told you, due to homogeneity and isotropy, we have the invariant. So the coordinate is invariant in any direction, right? So when you have the invariant in any direction, if your coordinate do not depend on the theta and phi, then you can choose polar coordinates. So usually in cosmology, instead of choosing this one, we choose this guy. If you have the flat space. What if you do not have the flat space? What if you have a positive curvature, right? So if your universe is positively has a positive curvature, then what is the definition of a positive curvature? The positive curvature, 4-dimensional Euclidean space, is defined as x square plus y square plus z square plus some w square is equal to r square, right? So suppose if you have a sphere and this is the center of the sphere, all the points from the center of the sphere have the same distance. And this is what we define as the positive curvature. The surface of the balloon is a positively curvature. Okay, if you do the transformation, if you write it in the polar coordinates, and this guy can be eliminated using some transformation. If you use in polar coordinates, you can see that ds square can be written as some r square minus r square, dr square plus r square, d theta square plus sine square theta d phi square. Okay, if your system is positively curvature. We can do some more transformation, and I will tell you why. But in general, you can just write these things. You could take r square constant, define some another guy called chi plus sine square chi d theta square plus sine square theta d phi. How about the negative curvature? So how about the negative curvature? So for the negative curvature, you define as so this is the negative sign. And this is called a hyperbolic geometry. So this is called hyperboloid. Three-dimensional hyperboloid. If you do the same thing, you get the same metric, but instead of sine, you have sine hyperbolic. And if you use this geometry, then you mean that the geometry of your space-time is negatively curvature. This has a negative curvature. So in cosmology, the starting point in cosmology is this metric. You don't know about the geometry. So what you can do, because we don't know about the geometry, well, from observation is the flat geometry, but it could be positively or negatively curvature. So what we do, we start with saying that, well, we don't know about cosmology curvature. Let's write the most generic metric, right? So the metric of the universe we write is something like ds square is equal to some r square d chi square, right? Some k chi d phi square with this guy s of k of chi is equal to, if this is sine of chi, then your k is equal to +1. Okay, if it is chi, then k is equal to 0. Is a sine hyperbolic of chi, k is equal to -1. So this is the positive curvature, this is the flat, and this one is the hyperbolic or negative curvature. So this is the geometry without the time coordinates. You can just put the time coordinates straightforwardly, but the space is the geometry of the space-time in cosmology. You start with this metric, and this is a very important metric. And this metric, if you include the time coordinate, if I include the time, and remember the time coordinate, we always have ds square minus c square dt square plus some dx square. So if I include this coordinate, what I get is ds square is equal to minus c squared dt square plus a squared t, okay, 1 divided by 1 minus k r square dr square plus r square d theta square sine square theta d phi. And bear with me because this is very important equation. This metric is called FRTW metric. It's called FRW metric. Friedman, Robertson, Volcker metric. In this metric, c is the space is the speed of light. This k defines the curvature. So it could be +1, it could be 0, it could be -1. Okay, r is just the r is the curvature. So k is the sign of the curvature, r is the curvature itself. And what is more important in this thing is this thing, a square. A is called the scale factor, and a depends on time, which means the scale factor depends on time. And when the time is increasing, your metric is increasing, your space is increasing, right? So a is multiplied by the spatial factor, but not the time factor, which means that when the universe is evolving, the time is the same thing. Time is just the linear. but the space is multiplied by a factor which depends on the time. So with time, this factor A increases, and so your your space is increasing, and therefore this expansion of the universe depends on this factor called A, right? Scale factor A. So this is the most important thing. If you start with anything in cosmology, this, I think this guy, this metric is the most. Yes, Hassan.
Sir, can I ask a question right now? Yeah, after a little while.
But like, give me 5 minutes. I'll just finish it, and then
Sure,
we
sure.
can ask the question.
Sure.
Okay, so this coordinate, and just to give you an idea of what it looks like. So if you have the space, for example, like this, okay, with time, it will increase. And this is just a multiplied by A. So A is expansion. So this is what you call the expanding universe, right? So because the universe is expanding, and therefore we have this metric in this thing. A is a convention, A naught, which is defined as A T naught is equal to 0, where T naught is the present time. Okay, so the present time we defined like this. Sorry. So consider a galaxy sitting at some fixed point r, theta, and phi. So suppose there is a galaxy at this point with r, theta, sorry, phi. We refer this coordinate or equivalently chi, theta, phi. I mean, if you use r or chi, theta, phi, but chi depends on r, we call it co-moving coordinates. And you will always read the word co-moving coordinates in the cosmology notes. Okay, and they are analogous to the Lagrangian coordinates used in fluid mechanics. The physical distance between 2 points and the origin. So if you have this galaxy, and suppose you're observing from here. Okay, so this is your observer, and suppose you choose your coordinates such that you are at the center of the coordinates. So what will be the distance between you and the galaxy? So right, so what will be the distance between the origin and the galaxy, which is sitting at r, theta, phi coordinate? This distance is called the physical distance or the proper distance. And you define this distance like this. You have this physical distance, okay, is equal to A of t integral of 0 to r 1 divided by 1 minus kr prime square divided by r square dr prime square, which is equal to A of t r of chi. Okay. So where k is the sign, r is the curvature. Given any geometry, any curvature, if you want to find the distance, how far the galaxy is, you choose this coordinate, this example. Okay. So the rest of the things, I think, for now, I think for this lecture, I think this is enough. We have the concept of for the next time. I think we can discuss about things like Hubble parameter. What is Hubble law? It's very important. We will discuss about redshifts. It's the most important thing in cosmology. Everything is measured in redshift. I can show you the. I will tell you about the concept of the horizons. What is the physical horizon? and event horizon, and actually Hubble horizon as well, right? So I'll discuss more about conformal time. And the distances, like the luminosity distance. How do you define the distance? And these are very important, the Friedman equations. Because once you have the Friedman equations, and you can understand the dynamic of space-time. You can understand the dynamics in cosmology, the evolution of the cosmology, different factors that push the evolution, metal domination, radiation domination. And once you have understood these things, hopefully it will be easier to go and maybe understand about the concept of inflation. And when you do the inflation, then we will not have time, but I'm just writing it down, like what are the most important statistical estimators, such as power spectrum, bispectrum. And then after understanding power spectrum, bispectrum, you can do cosmological perturbation theory and structure formation, which depends on cosmological perturbation theory, how structures and galaxies and formation. Okay, so these are the things. Maybe I don't know if we will have time next week to cover all these things, but these are the most important things. I think the Hubble's law, redshifts, horizons, conformal time, luminosity distance, Friedman equations, which defines the dynamics of space-time, inflation, what are the statistical estimators, how do you extract statistical information from the inflation, from the fluctuations in the inflation, or also fluctuations in the CMB. And then once you understand what power spectrum bispectrums are, what are the cosmological perturbation theory, and how we can understand the structure formation based on the cosmological perturbation theory. And once you have understood all these things, I think it will be easier to understand the current state of the research in cosmology. But we will see what we can cover next week. If you guys are okay, we can arrange another lecture, maybe somewhere in the week or later.
Yes,
But
that would be great, sir, especially because we have missed one lecture last time. Or we could even have a longer session the next time.
That could be the case. We can have a longer section next time. Yeah. So I can share these notes with you guys, and some other things. I think one of the So these are the notes which are really good, but I can also share you also the other notes later. Hassan, I will send you the email and I will share all these notes and the materials, and you can forward. Okay, so any question? No, I think people have left already. No questions?
Sir, it's people have left because there have been power outages. Some people have classes, quizzes scheduled, because this is like the last working weekend.
Sahi hai. Okay, sounds good.
So next time, sir, there will be more people will join. Hopefully, because this was like lectures are also scheduled during this week. we can say.
सही. So was it okay the mathematical thing? यानी कि ठीक था इसमें, यानी इतना सिंपल था, आसान था, मुश्किल था, क्या बोरिंग
Yes,
था?
sir. I think it was all right because we have done linear algebra. Most of the kids here have done linear algebra, and so it was fine. And we have also a lot of us have also done modern physics.
अच्छा, क्योंकि मुझे अंदाजा नहीं होता कि अगेन हमारे पास टाइम भी बहुत कम है और ये कॉन्सेप्ट्स भी बहुत ज्यादा थोड़े मुश्किल हैं, लेकिन अब जितना मैं हो सकता था मैंने मुश्किल सिंपल सा बता दिया, बट आई एम श्योर कि
नहीं सर, बहुत
ये
हेल्पफुल था एक्चुअली.
लगेगा.
हाँ, I get it, sir. Actually helpful था because it's kind of like an overview and we could go into the notes to understand these concepts better.
हाँ, तो उस लिहाज से चलो फिर नेक्स्ट टाइम हम लोग का मिलते हैं. नेक्स्ट टाइम फिर we will discuss more. ठीक है?
Sure, sir. Sorry about the low attendance today, sir.
चलो कोई मसला नहीं. नेक्स्ट टाइम
और लोगों की डिस्कनेक्ट हुए, इंटरनेट लाइट चली गई थी इसलिए लोग डिस्कनेक्ट हो गए.
सही.
ठीक है.
ओके, फिर मुझे अपना सेंड कर देना तुम वो कवर लेटर जो भी है.
जी श्योर सर, मैं आपको सेंड कर दूंगा. थैंक यू सो मच सर. सर आप कब तक एक्टिव होते हैं? मैं आपको होपफुली विदिन 2 आवर्स या 2-3 आवर्स भेज दूंगा मैक्सिमम.
हाँ, मुझे भेज देना. अभी तो मैं उठा हूँ, मैंने क्या कहते हैं कुछ दूसरे काम भी करने होंगे, तो आई विल बी फ्री.
श्योर सर. थैंक यू सो मच.
ओके, नो प्रॉब्लम. अल्लाह हाफिज़. बाय.